Herminso, the floor is yours.
Thanks for the kind introduction. So let's get started. I like to start this presentation with a slide that summarizes the history of X-rays from medical applications to non-destructive evaluation, specifically including some applications for inspection of electronic components and medical devices. And the main emphasis is on 3D reconstruction data. So meaning you have to reconstruct the full three-dimensional volume of the part. There are several types of X-ray systems that can do computer tomography. The more classical one, especially in the industrial setting, is composed of an X-ray source, a detector, flat panel generally, and a stage where you are going to put the sample to rotate and collect several projections before you do the full 3D reconstruction. Those systems function based on geometrical magnification, which basically means that wherever you put the part in this cone beam of X-rays, then that will tell you how much is the magnification of the system, and that will depend on the size of the sample, because the sample has to be within that cone. A little more advanced systems are the so-called X-ray microscopes, which also has the main base components, including the X-ray source, the sample stage, and the detector. But the difference is that the detectors work a little bit different by adding optical magnification. So in this case, the X-rays are collected by scintillator detectors right here in the front, and they get converted into light before it goes into a CCD detector. And you have the ability to rotate these lenses from one magnification to the other, just like in a light microscope. That's why we call them X-ray microscope. And to give you an example of application, let's say imagine we have a smartphone and we can scan, of course, the full smartphone and then start using the different optical magnifications to zoom in a smaller field of view at a higher resolution to see inside of the PCBs or the circuit boards inside of this smartphone to check for any defects that you might be looking for and see the connection of the vias between the different layers, or look for any signs of porosity that you might be concerned of. And if you want to go to a different region of the device, you just go, select the field of view and the lens that you need to scan, for example, a camera lens. And in this case, the application is to check for assembly analysis, how the different lenses have been assembled in terms of structural positioning, and also check some dimensions of the different gaps. This is quite important for generating high quality imaging from those pictures that you take with a smartphone. And as a last example, in this device, I'm going to show the inspection of a portion of the battery. And in this case, it's a battery that has been cycled through several cycles of charging and discharging, to the point that you can see degradation on the particles that compose the electrodes and some signs of delamination. So the typical workflow of X-ray microscopy is, okay, you scan the full device, and the X-ray microscope could include also a flat panel to do classical computer tomography. But then if you want high resolution imaging, you change the lenses and zoom in into the different components to see at a higher magnification. So you basically do a scan and then a zoom in with something that we call resolution at a distance or RAD, which basically means you can access the high resolution in different field of view without destroying the sample. So it's independent of the size of the sample. You know how to slice it, and you still get access to a smaller field of view at a higher resolution. And a little bit of fancier video is an explanation here with an apple, but you can imagine you have one of your devices, electronic component, and it shows what happens when you try to get the highest magnification in traditional computer tomography. Yes, it's possible until you are out of room here because the sample needs to rotate. So the only way to get higher resolution in this case, it would be to actually cut the sample. And even though if you do that, still because you're only using geometrical magnification, those resolutions are going to be limited to something in the order of 5 or 10 microns, depending of the chunk that you cut of the part. If we use the X-ray microscopes, then what we have is additional lensing here. So the X-rays just hit the scintillator here, then convert into light, then it gets magnified by the lens, and you can change those lenses and get a magnified image over the CCD detector. And that's how we are getting the power of resolution at a distance in these type of systems. The typical inspection workflow looks like this. You basically collect, after you get the setup in your instrument, a set of projections. Those are radiographs, as any radiographs that you take in a medical device. Then, but you have to rotate the sample, collect a bunch of radiographs in the order of 2,000 or more, and then get the 3D reconstruction. Once you have the 3D reconstruction, you can go through cross-sectional slices. Of course, these are virtual slices, it's not physical cross-sectioning, and so you can see inside of the part what is going on without putting the sample. That's a little bit of a summary of what we do with 3D scanning. And the main question is, okay, well, a lot of people do 2D, and why do we need to do 3D imaging? So I generally try to show an example here, and I say, okay, well, this is a question for you. We see an image there, a projection, and can you tell me what the projection represents in the real object? Any ideas?
A cactus.
It could be a cactus, looks like a hand. Any other?
I read the papers, I know what that is.
Okay, well, let me show you.
Turkey.
It is a bunny, trying to be funny. So 2D approach could be misleading, and that's true in circuit boards, because what you get in a 2D radiograph is an overlay of all the components that are in the back, in the front, in the middle, in a single image. And it could be confusing. Yes, it has still has application, and some people try to do some tricks and tilt the circuit board to see if they see some porosity. And this is in one example. It looks like there is a more transparent section here, and it could be a void. We're not quite sure. But if you do the 3D scanning and then do the cross-sectional slicing, then you will see clearly what is inside. So that's what 3D is really useful, is because it gives us the full information of the volume that is inside of the part. And that's how you can inspect for BGAs or PCBs, for solder bumps, micro bumps, fatigue cracks, coil joints or head on pillow, traces of electromigration, broken tiers, trace of cracks or cracks in the silicon components of the PCB. And of course, you can do this in finished devices like a smartphone or any PCB component that you might have to check all the typical examples that I showed in the previous slide. There is, I'm going to talk on different approaches to improve the imaging of X-ray, 3D X-ray imaging in flat samples. And in the second section of this talk, I'm gonna talk on some advanced reconstruction algorithms using artificial intelligence. But for now, let me illustrate some of the challenges when you have a flat panel, a flat sample. There is a challenge when you try to penetrate the sample with an even radiation because it's flat. X-rays pass very easily through here, but when it goes to this direction, it finds a longer path. So the intensity of the X-rays decrease, and that can generate some type of artifacts, which are called aliasing or undersampling. But in this case, it's more coming from the high aspect ratio. So even if you take longer projections, more projections, it's not going to quite solve this. And the way we have been solving this is by collecting more projections along the longer path of the X-rays to compensate for that. And that even, we can take less projections in here, improve the throughput or scan time, and get rid of those strict artifacts that you see when you don't use this high aspect tomography scanning, or HART. We're calling it HART for simplification. And you reduce the scan time and improve the image quality. And this can be applied for PCBs or circuit boards that go inside of finished devices, like in this case a smartwatch, to scan a circuit board or even the battery, because those batteries, and also for electronics, generally they are flat. They are so-called pouch batteries, as opposed to the cylindrical batteries that are more uniform in volume. With this, you could scan components from all the electronics, consumer electronics, but even automotive, including lighting, power electronics, connectors, displays, antennas, etc. Okay, so that's the beauty of the technology and some techniques we have done to improve it. Now I'm going to go to tell you how are we leveraging machine learning to even improve more the way we are reconstructing. And to do that, I want to make sure that it's clear where are we using machine learning. A lot of people use deep recon as a post-reconstruction processing. So once the data is reconstructed, they try to improve the data after reconstruction. That's a post-processing approach. We are using a pre-reconstruction approach. What we are doing is we are trying to leverage deep learning between the 2D radiograph and the 3D volume reconstruction to improve the image quality and speed the scan time by reducing the number of projections. And that's what we are doing. It's a little more simplified here now, but I wanted you to understand where in the full workflow is this deep learning process. You take the 2D projection data and use deep learning network models to try to differentiate noise from actual features of the data that you are interested in. And then get the 3D reconstruction to get a high quality 3D reconstructed volume. And that's what you see at the end with the scan of this pouch battery. I have examples for that, and I compare the typical standard reconstruction. By the way, the standard reconstruction is an analytical algorithm, so-called FELCAM or FDK. There are variations. It's an algorithm that was created in the 1980s, but it's still the most used algorithm in industrial setups. So what we are doing is, instead of using the FDK, we are using deep recon, and we are to be able to get a decent image quality with the traditional FDK, you need a large number of projections, over 2,000 or more. And the scan time can be quite long. If you use deep learning algorithms, you can reduce the number of projections, because now you train the network to identify noise from actual features and save time and improve image quality to the point that you can see more clearly the structure of the particles in the electrodes for this battery. The same is true for other types of components that can be scanned a little faster given the material composition. So now you only need in the order of 1,000 projections for FDK, but still you could reduce that by 10 times down to 120 projections and get great image quality using deep reconstruction or deep learning algorithms. This is what you will get if you use that small set of projections with FDK, and you clearly can see the strict artifacts that are generated by undersampling. Those artifacts are called aliasing artifacts. And an example for an electronics component in which you can see that the contrast to noise ratio is much higher here as compared to even what is here at the beginning with the full set of projections. And if you reduce the projections with the FDK, the data start getting lost in the noise. Okay, so that's if you try to do improvement in quality and scan time by using deep learning to do the reconstruction. There is another challenge with PCBs or circuit boards, and is they generally have a large field of view. And if you want to scan at a higher resolution, that's possible, but from the previous slide, you saw that there is a compromise between field of view and resolution. You can get higher resolution, but the field of view starts decreasing. So if you want to get high resolution, the field of view needs to be targeted in a smaller region. And if you want to scan the full board at high resolution, then you will have to type in the traditional way of scanning, start doing multiple scanning. And then maybe stitch the volume to be able to create the full high resolution scan of the full field of view. That proves too long. What you could do using deep learning algorithms is, okay, pick up a field of view with the high resolution you need, scan it, and then scan the large field of view at a lower resolution. Use this high resolution as a training model for generating a solution in deep learning, which we call DeepScout, and now expand that to the full volume to recover the data. And that will save all of these steps. So that's the second way in which we are able to leverage deep learning algorithms to do the reconstruction of X-ray microscopy these days. And this is an example for a large circuit board. It's a very long circuit board, and we scan as low resolution with traditional way of scanning. You can see it here. Then a high resolution that we can use for training purposes. And once the model is created, we can recover from this data the DeepScout data that is very similar to the high resolution. And if we apply the same model to the full field of view, then we can recover the full field of view at a higher resolution and save scan time and improve the quality of the data. So again, low resolution scan, DeepScout recover, and that you can see that this is allowing us to see more clearly where the defects are and classify them if we need to. And when you apply that to the full field of view, then this is what you get. And I think I have a video of that to give you an idea of what happened in the volume. This is a high resolution scan that is being used for deep learning training, and then once you get it, you apply it to a low resolution scan of the full field of view, and then you get improvement in image quality. I'll give you a second example. And this case is for a battery. This is a solid-state battery, and it's a very elongated battery. Here you see a low-resolution scan and a high-resolution in a small field of view. If you apply that, you can see the difference between the two types of scanning, and you can imagine that we scan this with a high-resolution lens, the other one low-resolution lens, and then we apply the training model to recover the full field of view using the high resolution scan. And then you can see that across the full field of view, the data has been recovered. And here is a comparison of the normal traditional way of scanning, low resolution, high resolution, and the DeepScout recovery. So as a summary of those deep learning processes, you can use it in two ways. One is to improve the reconstruction in a given field of view, and that's what we are calling deep recon, or DeepScout, which will use a high resolution, a small field of view as training to recover the data in a low resolution scan in a larger field of view. Now, we could also, additional to doing deep learning training, you could use some augmented reality settings that take a visual image of the sample and tell you, based on some radiograph settings from the X-ray system, determine what is the best way to optimize scan time and resolution. And you see two curves here, one that is for optimizing scan time, and this will be the optimal region of settings where you could get faster in terms of scanning. But if you want to optimize resolution, then this will be the region. And if you want both at the same time, you could just look for the intersection of the two curves, and the system will tell you more or less what type of setting you will need to do. And that's how you could scan going from one low resolution settings from one of those lenses to all the way to 4x or 40x to scan a small field of view at a higher resolution. And thus, on top of that, we also have done some developments on X-ray detection. Traditionally, for those that are familiar with X-ray, you can get high resolution specifications for a detector at a low kV settings for the X-ray imaging. As long as you, once you start increasing the kV settings of the X-ray source, then those specification of resolution start decreasing linearly sometimes, depending on the kV that you are using. With new detecting technology, we have been able to keep the resolution down. It still varies a little, quite little from what is the initial resolution and 30 kV. So you can use the 160 kV and still keep the low resolution on those detection capabilities. This is quite important because, as you can imagine, from PCBs or electronic components, they need a high kV for penetrating to metals. And I give you a couple of examples here so you can get an idea. This is collected with the previous way of scanning, the previous detecting technology, and this is where the new detector development using the 4XP detector. Now, if you want to increase the resolution, you will have to even modify the X-ray microscope and maybe use condenser lenses and Fresnel plates. In this case, you will need a sample prep because you see that it's a very small region. You will need to, in the order of 1 cube millimeter, to be able to scan this. And yes, you get gray imaging. It's destructive because you have to prepare the sample, but still it's 3D. You don't have to slide the sample, so it's not invasive. But there are challenges. The scan time can be long, and the image quality can be compromised by noise and sample motion artifacts. Now, we have deep learning algorithms, and if you apply those deep learning algorithms, then you can reduce the scan time of those long detection systems to something that is more approachable in the order of 4 hours, in this case, with 250 projections to get the best image quality that you can get. So this is kind of a summary of how you can go into improve the resolution on top of using deep learning algorithms. If you use the traditional submicron 3D X-ray detection, and that's not even enough, you can section a portion of the part and get a small feature that you can scan with a higher image detection that can go down to 50 nanometers spatial resolution. And this is a workflow for failure analysis, where you can go from a non-destructive failure analysis system, including 3D X-ray computer tomography, do sample prep, go to SEM, or if you want to conserve the feature, do an isolation of the feature, go to a higher X-ray microscope, nanoscale, down to 50 nanometers, and if that's not even enough, then go to FEM and other higher resolution SEMs, where you need now to slice your sample. And this is just one example of how we've done that, from going from X-ray to electron microscopy to identify at higher resolution the features. Of course, this is destructive, but no X-ray system is going to beat the resolution of an electron microscope. So I'll give you a little bit of a summary here of what we have talked today. Some improvements on ways of detect with X-ray microscopy for electronic components using resolution at a distance are deep learning, a couple of packages, DeepRecon, DeepScout, some operating system to optimize the settings, new detecting developments, nanoscale, tomography, and correlative workflows, which include SEMs. With this, I'll be happy to take any questions you might have.
Thanks. So if there is any questions, I think we have 5 minutes for questions.
Yes, please.
So when you're choosing your training location, do you have to be careful to get a good representation of the features that you're going to be seeing within that PCBA. So, for example, you don't want to choose a location that has zero voiding or too much voiding. Is that something that has to be accounted for?
Yes, you have to be careful with that, but more than looking for the voiding, I will look for the type of features. So let's say you're looking for VGAs, not looking too much for the vias, then you will try to do the training in a section that has that. Those might have voiding, and that will be ideal. X-rays basically work in terms of contrast, so what you tell is a void is because you don't see material there. So that will be great, but it's not necessary because you still will have other regions of the scan that will have no material that can tell what will be noise. And the way to optimize that is that the system tell you where there is no material, you can identify noise, get rid of it, and enhance the contrast. This is important to create a deep learning training that represents the component. So you're not going to apply a deep learning training that you use in a PCB to a battery, for example. It's not going to work. Yes?
Do you have an overall board thickness restriction?
It's more, it's not given by the deep learning algorithm, it's given by the restriction of the X-ray system. So the way X-rays work is once they hit the sample, there are a couple of factors that decreases the intensity of the X-rays that pass through. Those are density of the material and thickness. So, and it's like an exponential law of decay. So you can imagine that if you start putting heavier materials like steels or stuff like that, then the thickness start decreasing. And there are tables out there that calculate how much thickness you can pass through depending on the material. It not only depends on that, it also depends on the kV that you are hitting through the system. In the case I showed today, the maximum is 160. That seems to be okay for most PCB of circuit boards. But if you have some other type of material, like, I don't know, an Inconel additive manufacturing that is quite big, then you might need 450 kV or so.
Can you use the deep recon stuff to use phase contrast?
Yes.
Better images?
Yes, that's correct. In fact, we have developed a new package that is called Phase Evolve. Because you're using phase contrast, then it needs some additional inputs to be able to work. But yes, it's possible.
Any other questions? Well, I have one question.
Yes,
as
sure.
well. So can you record video of those as well? Like for the electromigration, that's something that I'm very interested in.
Mm-hmm,
And, you know, for the LTS that a lot of people are very familiar with. Now, one of the things is that this piston is just going, you know, around to the anode side when you have the current.
Mm-hmm.
Can you have like a recording, like how this thing is moving?
Oh, okay, like in situ, the evolution on time. That's possible, but you have one challenge, and it's the scan time. So if the process is happening so fast that you cannot capture that when you go through the 360 or 180 rotation, it already happened. Remember,
So you missed out.
you missed that. So you will. It has to be the process has to be slow enough, so you can capture several scans, 360 scans or 180, and capture that.
Sure.
What people have done is to do in situ stages to do testing. For example, compression test is an easy one because you can put certain compression, scan, then increase the compression, scan,
Sure.
and then you have the evolution on time. There are other packages for in situ testing in materials that can be done.
Very impressive. I really enjoyed reading your paper. Thanks for being here. Thanks
Yeah,
for
thank you
presenting.
for the invite.